Hi, my name is Jay Jacobs. I'm a chief data scientist and a partner at Scienti Institute. I worked on the Verizon DBIR, and I've been a data scientist for a number of years and working in security for 20 plus years. And so it's great to be presenting at RSA. My co-presenter, Ben Edwards, is a senior data scientist with me at Scienti Institute. He's got a PhD from University of New Mexico, and he will be joining, talking about some stuff later on in the slides, and I'm going to start out here. So what we're going to cover today, we're talking about application security and some of the fun things about it and some of the security aspects associated with that. And so this is going to be a very, very data-driven talk. And so we're going to talk about a lot of application data, a lot of flaws, and the fix times, and a whole bunch of stuff. And so first, we want to cover where this data came from. And then that helps establish, the frame, set up any potential biases in the data. Then we're going to talk about just sort of an introduction, set a foundation about how secure are applications. And then we're going to talk about a little bit about remediation, fix times, things like that. And then we're going to get into how does the language, the development language, affect security, and what do we see across different languages? Then we're going to get into some open source stuff, talk about open source libraries, third-party libraries, and inclusion in the applications and what that does for security. And then the best part, I think, of the whole talk is going to be this last section where we talk about looking at that remediation time and look at attributes that can contribute to faster or slower fix times. And that'll be the nature versus nurture part of the talk. So let's start out and talk about the data here. Essentially, we're looking at 130,000 applications, over 130,000. And depending on how we slice it, it'll be a little bit less than that, depending on what we're looking at. But this is all coming from Veracode customers. And this is a lot of this is covered in the volume 11 of State of the Software Security Report, which is free to download. But we've got this bias in there that these applications are from organizations that are vested in security already. And so this might be perhaps overestimating some of the security aspects because they are already putting money into and putting their time into security aspects. And so just got to keep that in mind. Might actually be that the whole world might be a little bit worse than the data we're looking at. But I think that's good. I think that we're looking at sort of a best case of companies actually investing in security. We have over 1 million code scans over the amount of data we have here, and it's a lot of data. We have over 10 million findings, that is flaws that have been found, typically from static analysis, although we're going to look at some dynamic analysis stuff too. And one of the things that we're doing is that we're going to analyze the full history of any active applications. What we've done in previous State of Software Security reports is sort of look at the last 12 months. And this year, we're taking a look at the full history from when an application came on board for the first time to the last time it was scanned right before we pulled the data. And again, this is volume 11 of the State of Software Security Report through Veracode, and we are not employees of Veracode. We are independent researchers that work with Veracode on this. So let's get into the actual security aspect here. So let's first talk about how common are application flaws. If you think of an application, what is the chance that static code analysis would find some type of flaw in it? And so most applications at some point or another have at least one flaw. And then this is completely independent of application size. So this might be 10 lines of code for a small quick library in JavaScript, or it could be 10 gig of files in Java. And so could be any size. And so across there, obviously the larger apps are going to have more flaws, but just blanket, regardless of size, what we see is about 3 out of 4 will have some type of flaw. But on the bottom side, we see about 1 out of 4 has high severity, and that's higher critical severity ranking in the Veracode platform. The middle two, if the flaw is one of the things listed in the OWASP top 10, we see about 66, 2 out of 3. 66% of those have at least one OWASP top 10 flaw. And then the SANS top 25, but I think that's now the CWE top 25. But when we're looking at it, it was still the SANS 25. And we see about 60% of things have things in that top 25 from SANS. So And we're seeing that relatively consistent, even from volume 1 up to volume 11, hanging right around that 3 out of 4 applications have at least one flaw. Now, when we take into account the size of the application, we see some really interesting things here. If you notice, these are trying to show the distributions, and it's the number of flaws per 1 megabyte of code. And this is going to vary based on the language, things like that. Some are a little bit more dense, some spread out. But the cool thing is, if you notice the distributions here, you see how they're pretty smooth. I think that's a really interesting thing. And that's partially an artifact of the amount of data that we have here. And that it's just sort of a smooth distribution from basically 1 in 100 million. So if you look at the left to the right, we're seeing things going from relatively not dense at all, a whole bunch of code and very few flaws, to on the right side, we see a whole bunch of flaws and perhaps not much code. But again, we're seeing that distribution. Any flaws, there's a lot more. On the critical flaws, there's less, but there is this wide distribution. That's what we're trying to get at here. There are some that have a tremendous amount of critical flaws for the amount of code that they have. So, and that's sort of what we're getting at there. So getting away from sort of these general statements about flaws, we want to take a look at what flaw types are most common. And so at the top here, what we see is things like information leakage, CRLF injection, and some of these aren't critical. And we have another problem too, as we classify these. These are taken from CWE, the common weakness enumeration, and that trying to put these things in a bucket is very difficult. And so if you take a look at something like insufficient input validation, the sixth one down, that is sort of a blanket catch-all. But if you take a look like CRLF injection, directory traversal, cross-site scripting, SQL injection, all of those are also insufficient input validation. And so it's a little bit hard trying to keep them in their own bucket and things like that. But we see a lot of that up front. We see a lot of that insufficient input validation. So that's one of the key things, and that's obviously in the top 10 for OWASP and things like that. Some other interesting things, obviously, some of these have been around for so long, still talking about them since the dawn of time. So like on the bottom, we've got buffer overflow, buffer management errors, things like that. They're still around, but what we're seeing is that some of the languages make that a non-issue. So, buffer overflow in Java, it's a really tricky thing to get in an application to have that happen. But so it's interesting just to see this distribution and talk about them. Now, we can also look at how dense are these flaws in the code. So again, we're going to look at the percent of applications with the flaw type across the x-axis, the horizontal, and then vertically up and down. Things that appear more often in application are going to be higher up, and things that appear really infrequently are going to be lower down. So like in the top right, we've got CRLF injection. So it's in a lot of applications. And when it's in an application, it's in there repeatedly, 10 to 11 times on average across the application. In the upper left, you see coding standards. When it's not in a whole lot of applications, but when it's in there a whole lot. And so it's just interesting seeing this sort of flow from not a lot of apps, not a lot of spread in the application up to the upper right, where it's in a whole lot of applications, and we don't see it, or we see it a lot more in the density. Now, this is taken from the report, and what we're talking about is these flaws. And so you might be perceived the best thing here is to just not put in the code in the first place, which is good, but really for security teams, for DevOps, for developers, what you want to do is be able to recover and fail safe here on these flaws. And so you want to be able to remediate these flaws quickly and thoroughly. And so we're going to talk about how spread out are these time-wise, how long does it take to remediate, and then how many are actually being remediated. So when we take a look at that, this is how many are actually fixed. So out of all the flaws on the bottom, roughly 72.6%, 73% of all flaws will eventually be remediated, which means roughly 27% are still open at the time we pulled this data. And that's gonna remain relatively constant. We're gonna have flaws closed out, but we're gonna discover some new ones. we're probably going to hang right around this ratio. And then you look up to like high severity, 82%, roughly about 7 out of 8 are going to be fixed, but we still have roughly 1 out of 8 sort of hanging out there. And so it's interesting to think about, and it's always hard. There's always going to be flaws out there that we want to go after. And if we talk about over time, we're going to get into time a little bit more later, some of the actual speed of remediation. But this is going to look at the capacity to remediate. And so if you think of an application as a living organism, we want to know, are applications generally reducing the amount of flaws, the flaw density that we see in the applications, or are they getting worse? Are they adding a bunch of features and a bunch of code in there and actually introducing more bugs? So what we see is when we look at all flaws, actually across all of these categories, there are more applications that are reducing the amount of flaws than that are increasing the flaws, the yellow on the right. And then a lot of them have no change, especially as we get to high severity. A lot of them just either close them out right away and just keep them closed, and anything new comes up, they close them right away. So they're mainly maintaining the flaw density of high severity, hopefully at 0. But we do see on the right, we see these features being added, things like that are increasing the amount of flaw density in applications, which isn't necessarily a great thing. So, and so it's nice to see the spread, though. There's a lot of variations, a lot of variety in these applications. And let's talk about the language, though, because this, I think, gets into an interesting aspect, because a lot of people will generally stick to the language that they know, and or they're used to something, and so they focus on that, and we'll get new applications in there. And so when we look at the type of languages that we see across industries, largely we see Java and .NET. Those are dominating the landscape. It's a little interesting since we see government sort of as a oddball here, second from the bottom, where we see more .NET than Java. Otherwise, we almost exclusively see more Java than .NET, but those two are absolutely dominating. Then we see some JavaScript in the third place. Roughly 1 out of 6 applications are JavaScript, depending on the industry, and then the others, and that's Python, Android, PHP, C++, and there's Ruby, and just a whole bunch of other languages sort of going along that tail there. Now, if we take a look at the top 10 flaws that we saw on that bar chart, I think these are most of the top 10 there, but we're looking at these top 10 across the languages. And so what you notice right away is that none of these look the same. So these flaws are going to be very, very different across languages. Like in Java, you see that CRLF injection, cross-site scripting, the upper right. When we look at PHP, you just see the cross-site scripting. Python, most of these specific flaws are down in the lower left, meaning not a lot of applications have it. When they have it, they're not very intense. They're not very dense in the application. But when we take these languages and look at the top 10 within each language, we get a very different story here. And I think this is really, really interesting. So first, you can notice with the red being a high proportion of applications, that PHP really sticks out, that there are a lot, roughly 3 out of 4 applications have had cross-site scripting problems when it's written in PHP, versus something like JavaScript, where cross-site scripting is also number 1, but roughly, under a third compared to 3 out of 4 for PHP. So you see some really stark differences here across the languages. And even looking across the top 2, like .NET, you see information leakage and code quality, and the third one being that insufficient input validation. C++, error handling, and buffer management. Even though there was a small proportion overall of the flaws, it is a huge thing in C++, that buffer management. In Java, you have that CRLF injection problem, code quality, and the information leakage, similar, to .NET and some of those. JavaScript, we get the cross-site scripting as well as PHP. Python, we get some cryptographic issues in the cross-site scripting. So depending on the language that you like to work in and tend to work in, you're going to want to be aware of different things. So you can't just look at here's the top list of all vulnerabilities or all flaws in code. You're going to want to say, hey, since I work in JavaScript, I have to be more aware of cross-site scripting, credential management, CRLF injection, than say someone working in C++ or something like that. you'd have a different focus. And this is the same exact data shown, just slightly different. But this again, like really highlights PHP. So if you notice PHP, that sort of darker green one is, what is that? Cross-site scripting in the top. And if you follow that dark green, you can see it's sort of hovering between 20, 25%. Most apps goes up to 30% for JavaScript, but largely down there, except for PHP, it jumps way up. And so this is just sort of fun to look at this particular one and see how it pans out across the languages. All right, and now we're going to talk about some third-party and open source libraries, and I'm going to pass it over to my partner, Ben.
And I'd like to thank Jay for that. We are going to talk about third-party and open source libraries because as we were doing this analysis, we realized that, of course, all this code is not written by the developers in-house, and we probably want to think about the effect of open source libraries and the flaws that they introduce. So, of course, the first question that we want to ask is what proportion of applications are actually composed of third-party code versus in-house code? And so what this chart shows is it's really variable. And of course, as Jay said, language matters. So across the horizontal axis is the percentage of the application that is third-party code or open source code, however we want to call it. And each dot here represents 1%. And so what we can see, again, we have this huge variation in languages. Java, almost all of the density is far to the right, where we have most of the applications are almost 100% third-party code. And then it kind of tails off far to the left. Of course, there are some Java applications, at least 1%, that are written totally from scratch, but it is generally pretty rare. And then we have things like .NET, where it's more spread out across there. JavaScript, we kind of have this bimodal, lots of things at 0%, lots of things at 100%. And a lot of this starts to make sense when you think about how these languages are constructed. So for Java, when you bring in functionality, you're bringing down those classes. Somebody's already written it. You go to Apache Commons and you find the library and you bring it in. In a large part, so with JavaScript as well, lots of very small libraries that you're including. And so that leads to this large percentage of code that is open source. Now, if we go down to C++ and kind of surprisingly PHP, most of those applications are written from scratch. So there is some library use, but the bulk of the code is actually 0%. And so this should totally not be surprising to us, right? Because of course, developers don't need to reinvent the wheel, or as we're saying here, reinvent the B+ tree every time they need a new data structure. So the B+ tree is kind of an example for me, because my sophomore computer science class, our professor asked us to implement a B+ tree on disk in C++. And realized that it was incredibly hard for sophomore computer science majors, and ended up actually saying, well, you just use a library for this anyway. And so obviously, like when developers find a problem that requires difficult coding, performant code, they're going to go reach for a library. And that's really an obvious boon. But it has its inherent risks. And so we want to start asking some of these questions, like how is free and open source software used in applications? What parts are used? When do they come in? What are the flaws that are introduced? Jay talked a lot about those flaws that are introduced in homegrown code. We want to know more about the open source code. And then once we know about kind of the landscape of those flaws, how do we manage it? How do we manage it? Because as Jay said, it's not just a matter of fixing everything, because we're never going to fix everything, but it's a matter of prioritizing and getting the right things fixed to make the application more secure. So to that end, I am going to tell you about, we wrote a different report, the State of Software Security Open Source Edition. I'm going to touch on some research that's in here and some that was not published in here, but there's a lot of good stuff there. If you want to go take a look at that, if you're interested in this part of the talk and want to go take a look, there's great information there. But probably most importantly, like language matters, as we've seen before in open source use as well. Most flaws are not serious. We're going to get to that. And of course, there's a large variance across open source use by applications. So let's get to that first question, and that just asks third-party libraries, like, how many are you using? So if we take a typical application off the shelf and say, like, how many libraries do you actually import? The answer, of course, is highly variable. So there are some JavaScript applications that we looked at that have thousands of libraries. And as I said before, this is not totally surprising. If you'll remember, there was a debacle a few years ago concerning a library called LeftPad. And it was a library that had a single function. It pads out a string on the left side of the string. And a developer pulled it off the package repository, the Node package repository, and broke a large number of applications because people were relying on this very simple one function library. And that's kind of what the culture around JavaScript and the ecosystem of JavaScript is. Very small functionality packaged up in a library. And that leads to high numbers of library use when you build these applications. Now, if you go down to something, say, like Python, where the libraries tend to be larger, more functionality, we get kind of lower numbers of imports, lower number of requirements that get pulled in. So, 16 is kind of typical, but all the way up into dozens. And as you can see, there's a large variability across all of these. And a lot of applications have, there could be several orders of magnitude difference between different applications. And so, once we've seen all those libraries, the next question we might want to ask is, how exactly are those libraries getting into the application? Are they coming in because the developer is saying, yes, I need that library? Or is it kind of this more of a backdoor, this transitive dependency where a library has actually called another library, which has called another library, which has called another library? As I said, it's libraries all the way down. And so we call those transitive dependencies, things that come in based on other library calls. So we wanted to look at, so for each application, look at kind of the balance between those two types of dependencies, direct and transitive. So what we did is we classified each application as either kind of direct heavy, transitive heavy, or balanced. And we broke this up, I think, into thirds. And again, we can see a huge difference based on language. For .NET, almost all applications are really direct dependency heavy. About 90% of applications, almost, the vast majority of includes are direct. And then again, down at the bottom there, Ruby and JavaScript, these kind of web-based languages, a lot of those dependencies are transitive. So you have these big trees that go out and all the transitive libraries come in and give you that weight. And so this makes a difference because if you are looking at it from a security standpoint and you want to know where flaws are coming in, there may be a lot that are included that you're not directly including. So you may hear about a flaw in an open source library and you think, I don't use that in my application, but it might be getting sucked in through some of your other dependencies. So it really is something to think about, is that, it's not just what you use, it's what you uses, and so on down the line. So what kind of exposure does this actually give applications? And this leads us to the question, is more libraries really more problems? And the answer is, yeah, generally, but it doesn't have to be. So what this graphic shows, again, broken out by language, because again, we know that makes a lot of difference, is on the horizontal axis is the number of libraries included in the application. And, as we said before, this can be up into the thousands, depending on the language. And the vertical axis is the number of flaws introduced by those libraries. So, and this is only open source flaws. We're not talking about homegrown flaws. This is the stuff that the library brings with it when it gets included in the application. And I think there could be a lot said on each segment of this graph, but it's important to point out that we do have this kind of, it's linear, but on a log scale. So sort of a power law relationship for languages like Java and JavaScript and Python in particular. And we can, why that's the case, why it scales like that is, there's some interesting questions. But I think, one of the big takeaways here is, yes, generally, if you include more libraries, you're increasing that risk surface. You may have more flaws, but it doesn't have to be. So in particular, if you look at kind of the lower left corner of the blob in JavaScript, you'll see that there are applications that have thousands, literally thousands of libraries with only one or two flaws induced by those libraries. And so if you've got this huge ecosystem that you're pulling into your application, it may still be manageable if you're doing the right things in the background to manage those flaws. And the same thing can be said for a lot of these other applications. The lower right-hand corner of Java, there's applications with hundreds of libraries, almost no flaws. .NET has a lot of libraries with no flaws. And so you can manage this issue. So the next thing we wanted to ask is like, how dangerous are these flaws? And we wanted to kind of build up a hierarchy of how rare they are and how important they are. So you can think of this bar graph as kind of like a funnel. So at the top, it's the percentage of applications that have just kind of any open source library that has a flaw, and that flaw is still open. And what I mean by open is it means the developer hasn't addressed it in any way. It's possible to have an application that has a flaw and the developer says, I'm not going to worry about it, close it, don't worry about it. But what we see is if you include open source libraries, you're really likely to have at least one flaw. So but the question is, how much should I worry about any particular flaw? Well, it turns out about 50% of applications have flaws that have a proof of concept. And the way we figured this out is we partnered with Kenna Security and got some of their data. And they have information on when a particular library has a vulnerability. Has there been a proof of concept that exercises that vulnerability published? And about half applications have that. So the next level down is worrying about, well, it has a proof of concept, but are attackers actually using it? And that's at 25%. So that is proof of concept, and we've seen it exploited in the wild. And so about a quarter of applications have this kind of higher level. And then last, there's one piece of information, another piece of information we get from Veracode, which is that library on the executable path? So is the flaw that's included in that library actually able to be exercised by an attacker? Now, this is a lower bound because it is impossible to say exactly whether every flaw is reachable or not in the code base, but it does give us an idea that actually this is pretty rare. So having a flaw in a library that is being exploited in the wild and is accessible by attackers is only 1% of flaws. So that's good news for us, right? So even if you have hundreds or thousands of flaws, this gives us a way to kind of look at prioritization and think about which ones we should address first. Now, that begs the question of like, how should we address them? And of course, the easiest answer is you just update things. So in particular, what we wanted to look at is how hard it is to update a library to a version without a flaw, and what kind of a big jump that was in the semantic versioning sense. And the great thing is more than 80% of library flaws can be resolved by just updating the library. And that update is really small, like, less than 2.1, less than that minor version. So about 20%, you are going to have to jump from 1.0 to 2.0, but that that'll depend on the application. Hopefully it doesn't break the workflow, and you can find a way around that. So I know there are some of you out there who might be scoffing and saying like, hey, it is never, of course, that easy. Once you update the library, that may introduce new flaws. And then those new flaws have to be updated, and then you're in this endless cycle. So we took a minute to try to think about what those cycles could look like and what the chain of updates can look like. And so we came up with 5 classes, 2 of which end in a final update. One is a single step and one is multi-step. You can do the same thing and kind of not end up with a version that doesn't have any kinds of flaws. Either there isn't one available or you take a few steps to get there. And then there's this rare thing that actually came out in the data that we had to look for, which was, is there a circular update? So sometimes the recommendation when there's a flaw is that you should kind of downgrade and go to a previous version. But if you do that and that version still has a flaw, you may go down the train a little bit before you jump back. So just looking at like how often each of these occur, we get some more good news. So most of the time, 2/3 of the time, you can fix flaws with a one or several steps, broken up to about 1/3, 1/3. So that's great. So most of the time, you can get to that endpoint where you're including a library with no known flaws. And then those circular updates, those bad ones that kind of are the most complicated and icky, are vanishingly small, about 0.5%. So we're lucky on that end. We wanted to do kind of a more complex breakdown, thinking about kind of where these things fall in this bar graph. So if we think about these different classes and where the size of the versions end up, because I did tell you that 80% are minor patch or smaller, but that may not be the case for these kind of update chains. So we wanted to look at that as well. And it turns out that actually most of the updates are still pretty small. So again, 70 a good percentage of flaws are just a pretty small update, and then 2/3 of those, end up in a clean state once you've done enough updates. But the nice part is 75% of those 2/3 are still minor version or less, minor version or patch. And so we do get this nice, even though you may go down this update chain, it's still going to be small. You're still not going to do too much. And so we can kind of fix open source. And thinking about open source, we've given you a lot of detail, but that's a practice for developers to kind of look at and be thinking about as they're developing their apps. And so to break that down and kind of tie all the things we've talked about today together, I'm going to throw back to my colleague, Jay.
All right, thanks, Ben. We're going to get into the really fun part of this and talk about nature versus nurture and the type of attributes and aspects of development and applications that will contribute to either faster or slower remediation times. So the first problem we have is trying to measure how fast flaws are getting fixed when we talk about that time aspect. And what we see is that one of the super easy ways is looking at the top line here, where this is a distribution of flaws and that were closed. And this is a really easy way to say, how long does it take to close something? Well, you can look at everything that's closed and figure out the median is 86 days. The problem with that is that when you start with a whole list of flaws, you don't know which one of those are going to be closed. And then you have to consider the bottom line here, which is the open findings. And essentially, these are flaws that were found and are still open. And the median open time here is 216 days and getting longer. So the question is, are the flaw that you see at day 0, is that going to be part of the closed findings and closed on average of 86 days, or is it going to stay open for over 6-7 months on average? And so the challenge is you can't just look at the closed, you have to account for these open findings. And you do that through a set of techniques sort of under the umbrella term of survival analysis. And so with that, we can take a look at all of the flaws, even the ones that are still open, and account for them in the probability that something will be fixed in some time period. And so when we take a look here on the top left, this is where 100% of these flaws are still open. And so in the first roughly 32 days, the first month roughly, about 1 in 4 of those flaws will be closed. And so what we're seeing is in that first month, a lot of activity. The line is really steep coming in there. And what we get is about 1 in 4 being closed. Now it takes another 5 months after that to get to half. So you can see the slope of that line is flattening out a little bit, and we get about half the flaws are fixed in the first 6 months. And conversely, after 6 months, half of them are still open. And so it's concerning, right? But we see this line flattening out, and it takes over 1.5 years to get to the next 25%, where 1 in 4 flaws still remain open after 1.5 years. And so we see this remediation, we see a lot of flurry up front. We see it going, in the first month, quarter of them are being closed, and it starts to slow down from there. And then 1.5 years later, we still have a quarter of them open. So there's some things we can look at, like, for example, if we look at the rate of scanning, how often is code scanning performed, and what kind of a feedback loop are we seeing? And in fact, when we see applications that scan very infrequently, what we see is that median, with if I go back here, the average is about 6 months. What we see for the applications that are scanning 12 or less times, we're seeing about 217 days, which is about 35 days faster or slower than the average. But then you see applications that are scanning roughly daily for every workday, over 260 times in a year. And we see those with an average of 62 days, closing half of their flaws, which is a dramatic difference here, right? So we see a huge shift. Now, what we wanted to do was to take all of these factors together, put them into a model, and see what they did to remediation time. And so we ended up gathering a bunch of factors of development, applications, the organizations they're in, and we threw them all into a model, and they sort of fit into these 2 categories of nature versus nurture, hence the analogy here. So you talk about the nature of applications, you've got the size of the organization. Generally larger organizations have more communication paths, a lot more complexity. Then you get, the age of the application. How big is that application? Is it complex and large, or sort of small and lightweight? The flaw density, typically known as security debt. And then on the nurture of applications, we've got how often is it being scanned? Is that scan cadence steady, or is it really bursty right around the last step of a waterfall method? And then do we see other aspects of security? Do they doing dynamic scans along with static? Are they doing SCA scanning? It's the software composition analysis. Do they have an API integration? In other words, it's part of their continuous integration, and they're part of like a code check-in as hitting the API and doing this code scanning. When we see all of that, this is the output that we see. We see this very simple bar chart that has a whole bunch of complexity on the back end. So we see things like at the top here, DAST with SAS, so the dynamic with static, that gets much quicker. And this is not saying that scanning dynamic will cause any of this. It's just saying, I think what this is saying is that teams that are dedicated to security are going to close things faster, and they're going to have dynamic scanning, and they're going to use the API, and they're going to have SCA. All of those contribute to faster things. That's largely probably some other attribute of that team that's really investing in security. But we do see frequent scanning, where you're scanning very steady. Those are also contributing. And what we see on the negative side are things like, the flaw density. That's the bottom one here. Roughly 63 days slower when you go up one standard deviation of your flaw density. If you remember in the beginning, we had those distributions. If you go one standard deviation off of normal, you're going to go 63 days slower. Conversely, if you get that flaw density below average, you're going to be 63 days quicker if you're a standard deviation above, with less flaw density. Larger applications, more complex, a lot of things in there. And if we look at the survival curve, that yellow one is basically bad nurture, bad nature, good, poor action, poor environment. But when you start shifting it and you get over to that very dark one, where you've got good actions, you're doing all the good things, and you've got a good environment, you've got lightweight applications, you're going to have a lot faster remediation times, and that's what bears out in the data. So let's jump into the takeaways. One of the first things is to sort of absorb this. I mean, like the bar chart that we talked about, the nature versus nurture, there's a lot of stuff in there. And think about your own applications and what you see. And then, so for example, the big things were security debt and the large applications. So consider splitting up large legacy applications. Look at microservices, look towards maybe spinning up some different teams, trying to split that out more. Try to drive down that flaw density too. So really go after that technical debt. You want to try and get some of these really bloated applications down and really close those up. And you want to improve that feedback cycle. We talked about that. So if you can get a team that's invested in security, you want to give them the tools to do that. And that's going to be more and variety of scanning, more tools to get more views and perspectives on that. And that's going to be really, really helpful. And you don't have to go commercial. There's plenty of open source options here too. And then, just make sure that this is part of the pipeline. You don't want to bolt this on afterwards. You want to make sure that as code gets checked in, as you're going through that pipeline, that security is part of that whole pipeline and integrated into that. And with that, we will wrap up and open it up for questions. And thank you very much for your time.